For thousands of years, humans have looked up at the night sky out of curiosity about what might be there, far beyond the reach of our most sophisticated telescopes and the limits of our imagination. But one daring mission, one robotic envoy, has traveled farther than any machine ever created by humans. In the seemingly endless expanse of the cosmos, countless regions remain unexplored and mysterious to human understanding. NASA launched the groundbreaking spacecraft Voyager 2 in 1977, and it embarked on an incredible journey that would take it beyond the planets and far into the unexplored outer reaches of our solar system. Voyager 2 is much more than simply a machine. It is the extension of human awareness, with our eyes and ears stretching out into the great reaches of the galaxy. What it saw as it reached the solar system's outer ring was nothing short of spectacular. Its main objective was to research the outer planets before continuing on its journey into the uncharted territories of interstellar space. But even after its scheduled planetary contacts were over, its importance continued. Today, we take a thorough look at what Voyager 2 discovered as it approached the edge of our unexpected readings. Voyager 2 continued to transmit vital information about the distant boundaries of the solar system and later about the enigmatic regions that lie in the vast interstellar void. Explained the solar system's remarkable discoveries and the unexpected events that surfaced as it traveled farther into space. The story of Voyager 2 began with its launch on August 20, 1977. Unlike its sibling Voyager 1, which took a slightly different path, Voyager 2 was created as part of NASA's larger plan to explore the outermost planets of our solar family. When Voyager 2 set out on a more extensive mission, it came into close proximity to all four gas giants: Jupiter, Saturn, Uranus, and Neptune. After completing its mission of conducting planetary flybys, Voyager 2 took an even more daring journey in 2018 when, after more than 40 years of traveling through the darkness of space, it crossed a boundary of great scientific importance. It left the protective bubble of solar particles and magnetic fields shaped by our Sun and entered the domain known as the interstellar medium. This unique trajectory allowed it to gather groundbreaking scientific observations regarding these planets and their accompanying satellites by 1989. This formal crossing, which took place on November 5, 2018, was just the second attempt by humans to go outside of our solar system. Voyager 1 was the first to do this in 2012, but what precisely is beyond this threshold? Definition of interstellar space prior to examining the experiences of Voyager 2. Unusual magnetic field activity. Understanding the importance of this environment is crucial since, for a long time, scientists used theoretical models and indirect observations to deduce what was outside of the Sun's primary sphere of influence. The area between stars outside of the shield created by our Sun is known as interstellar space. This zone, known as the heliosphere, is a vast shell surrounding the Sun where the solar wind, a continuous outflow of charged particles, prevails. Crossing the outer boundary of this zone, termed the heliopause, places a spacecraft in the interstellar medium. A completely different environment. Conditions here differ drastically from those within the heliosphere. Particle concentrations drop significantly and magnetic fields follow. Unfamiliar patterns for the very first time Voyager 2 was able to capture. Direct readings from this largely unstudied frontier. The momentous event of Voyager 2 breaching the heliopause on November 5, 2018 represented a historic leap for humanity. This invisible yet significant boundary separating the solar system from the interstellar medium had never been traversed by any spacecraft except for Voyager 1. The passage signified that Voyager 2 had now entered a realm where the Sun's energetic outflow no longer reigned. Instead, the spacecraft found itself adrift in the ambient interstellar wind, a mix of particles originating from distant stars and galactic materials. For scientists back on Earth, this moment was both a scientific triumph and a suspenseful test. Could the probe endure the unknowns of this vast region? More crucially, would it succeed in relaying information that could deepen our comprehension of this alien realm? The data Voyager 2 began to transmit shortly after entering the interstellar medium was nothing less than astonishing. One of the first unexpected revelations involved the concentration of particles. While solar wind particles had been prevalent at the solar system's fringe, Voyager 2 now registered a different population of particles. These originated. What is the heliopause? From the broader Milky Way part of the interstellar wind flowing between stars, remarkably, the probe detected that the density of these interstellar particles was about 20 times greater than scientists had initially calculated. This striking discovery reshaped scientific assumptions about what exists between stars, suggesting that the interstellar medium is far more dynamic and structured than previously believed. Alongside this, Voyager 2 encountered an entirely unfamiliar magnetic environment. The magnetic fields within our solar system are shaped significantly by the sun's magnetism. However, as the probe ventured further from solar influence, it began observing magnetic field lines that were governed by external galactic forces. This marked a significant advancement in our understanding of how magnetic fields behave outside the solar bubble. By analyzing these fields, researchers can develop more detailed models of our galaxy's architecture, gaining insight into how these invisible lines of force interconnect stars, interstellar dust clouds, and planets. The results of Voyager 2 showed that the interstellar magnetic field was far more complex than anticipated, offering crucial insights into the processes that shape the galaxy's structure and evolution. These magnetic fields are not merely anomalies. They also influence star formation, shape the interstellar medium, affect the motion of cosmic dust, and direct the trajectory of energetic particles through space. One particularly significant discovery was the discovery of cosmic rays, which are extremely energetic particles that come from apocalyptic cosmic events like supernova explosions. As Voyager 2 ventured farther into interstellar space, it came across cosmic radiation levels that were noticeably higher than those it had experienced inside the solar system. The effectiveness of the sun's heliosphere as a natural shield was shown by this increase in cosmic ray intensity. Astrophysicists' theories shielding Earth and other planets from these high-energy dangers. The spaceship was subjected to the full force of galactic cosmic rays once it passed through this barrier. These observations are extremely valuable because cosmic rays are known to affect not only electronics and spacecraft instrumentation but also possibly the Earth's climate systems and the health of astronauts on long-duration space missions. As a result, Voyager 2's data is crucial for preparing for future deep space exploration by assisting us in understanding the risks posed by cosmic radiation in unshielded environments. However, even though the probe's primary mission was to study the outer planets, its most significant legacy may come from its journey into the unknown as the spacecraft continues to plunge deeper into the dark of interstellar space, maintaining communication with Earth and sending a constant stream of data about this mysterious realm. As of 2020, Voyager 2 was still operational, offering insights into particle density, temperature fluctuations, magnetic fields, and radiation levels far beyond the heliosphere, but its nuclear power supply is limited. According to NASA, Voyager 2 will eventually stop communicating and gradually lose its ability to use its scientific instruments within the next few years. When that time comes, it will mark the end of an unprecedented chapter in space exploration, one in which human technology ventured beyond our solar cradle and into the endless void of space, even after it goes silent. The vast amount of data collected by Voyager 2 will continue to influence astronomy and space science for many years to come. Its findings have already changed our perception of the cosmos and raised fresh queries about the uncharted cosmos. Considering the remarkable achievements of Voyager, is something out there? It is clear that Voyager 2's interstellar journey is one of the most ambitious and captivating projects in space science history. The knowledge it has given us about cosmic rays, magnetic structures, and the properties of space outside the sun's reach has fundamentally expanded our understanding of the universe. But Voyager 2's mission is not finished. It continues its lonesome journey through the galactic wilderness, silently expanding humanity's reach deeper into space with each mile. Voyager 2 stands not only as a feat of engineering but also as a potent symbol of what humanity can accomplish when it is motivated by curiosity and bravery. It serves as a constant reminder of how much more is out there to discover in the vast ocean of space surrounding us. Although Voyager 2's contribution to the larger Voyager mission is sometimes overlooked in favor of its quicker cousin, Voyager 1, its scientific contributions from the start have been just as significant. Unlike Voyager 1, which focused on a faster route to reach the outer solar system in interstellar space, Voyager 2 was assigned to study the gas giants Jupiter, Saturn, Uranus, and Neptune. When it passed Jupiter in 1979, it took advantage of a rare planetary alignment that only happens once every 176 years, allowing it to complete a grand tour of all 4 outer planets in a single mission. Important information on the planet's magnetic dynamics, atmospheric patterns, and a close-up look at its biggest moon was recorded by Voyager 2. The Great Red Spot, a gigantic storm that has existed for decades, was also better understood and captured on camera by Ganymede, the probe. These discoveries set the stage for further Jupiter missions like Juno, which began orbiting the gas giant in 1981 and gathering its own data. More groundbreaking findings came during Voyager 2's rendezvous with Saturn. The spacecraft provided precise photographs of the planet's complex ring system and several moons, especially Voyager 2 versus Voyager 1. The most significant contributions of Voyager 2 were its flybys of Uranus and Neptune planets, which had never before been seen up close by any spacecraft. The data revolution revealed that Titan, Saturn's largest moon, contained a dense atmosphere rich in nitrogen, a finding that later served as the inspiration for the Cassini-Huygens mission. In addition to seeing the existence of tiny rings around the planet and obtaining atmospheric data that altered our views on ice giants, Voyager 2 also showed the planet's unusual axial tilt, which causes it to spin almost sideways in relation to other planets. The scientific community was further astounded by its 1989 encounter with Neptune. Voyager 2 became the only spacecraft to visit all 4 outer planets, permanently enhancing our knowledge of these far-off worlds. It also revealed Neptune's dynamic weather systems, including the Great Dark Spot, a massive storm system, and closely observed Neptune's moon Triton, spotting icy material geysers erupting from its surface.